So yeah, so we can start. So I want to thank a lot Paul Tappenden for accepting to give a talk here. I know a bit about this topic, so I'm very curious. I had a very nice discussion with him via email in the last month, so very curious to hear what you have to say. And of course, feel free to let me know if you want to ask clarification, in which case please write on the group chat or to me privately. And then at the end of the talk, of course, you can ask Q&A. We can have the Q&A. Since I think Simon might be leaving earlier, and also other people might be leaving earlier, if they want to ask question or comment, of course, I'll let them go first. I think that's pretty much it. So yeah, thank you. And last thing, sorry, can you please mute your microphone while he's giving the talk? Thank you. Okay, we can start. Thank you, Paul. Stage is yours.
Okay, well, thank you, Christian, for inviting me. It's a great opportunity, and thanks to everybody for being here. Let me just start to add a little bit of introduction for those of you who don't know me. I did a PhD at King's College London, and then I moved to France, which was a lifestyle decision. The result being that I've been working outside of academia ever since. But luckily, the internet arrived at the same time as I did in France, and so I've been able to keep in touch with the research community and get a few papers published. So these are papers I've had published in to do with Everettian theory. There's a key thought experiment which I'm going to be talking about today, which is a sort of jumping off point for the rest, which was in this paper, second from bottom right, objective probability in the mind-body relation. And that has been developed a bit further in the other two papers at the bottom, which were published about a year ago. Hold on, not scrolling. Oh, there we go. There we go. So I've also had a few papers in to do with philosophy of mind and personal identity. And this, notice there's this phrase, semantic internalist or semantic internalism there down the bottom right. That was the first paper in which the fundamental idea in all this was published, and this is what I'm going to be arguing is a profound link between quantum theory and philosophy of mind. There's been for decades a lot of debate in the Anglophone community, philosophy of mind community, about whether between semantic internalism and semantic externalism, and semantic externalism is by far the favorite, but I'm defending semantic internalism, as we'll see. So why am I here now? It's because I read this paper up at the top, which was Christian co-authored, and that was because I'd been reading one or two papers by Claudio Colossi as well, and so that's how I got in contact with Christian. And I read this Quantum Indeterminacy. That's this review paper which they both wrote together, which I think might be published now or is on the way to being published. And then at the bottom, a draft which Christian sent me a little while back. And so that's the contact. And it's all to do with a sort of line of research which goes back really to this seminal paper by Gareth Evans in 1978. And I think if this works, this is an outstanding example of how philosophy and physics can be mutually beneficial. Gareth Evans was a sort of become a legendary figure at Oxford. He died at the age of 34 from cancer, and his writings were put together in this book, The Varieties of Reference, which was published in '82. And I just heard a voice of it, I'll ignore it. So it says this in a review by Mark Sainsbury, who was professor at King's College when I was there. It will be central to discussions of reference and singular thought for years to come. Well, that's very much to do with issues to do with this internalism, externalism debate. So the link goes back quite a long way, but during the 80s, just purely within the domain of metaphysics and philosophy of language, this idea of could there be vague objects, fundamentally vague, not just sort of clouds or something like that, something metaphysically vague. And there was a lot of discussion about it. And then in the 90s, it suggested that perhaps quantum objects would be good candidates, being vague objects in that sense. And that led to a considerable amount of discussion, which went on into this century. And then around about 2010, this paper by George W. in 2010 seemed to mark, together with one by Jessica Wilson, 2013, a major sort of shift in direction of thinking. And so I've just given a sample of some of the papers, but there's quite a lot of papers. It's quite a sort of minor industry, and I'm far less familiar with it than Christian. There's certainly some sort of parallels and differences with what I'm going to talk about, but I think Christian would be probably better able to see them, talk about them than me, but anyway, we'll see. So here we are, metaphysical indeterminacy. What's this all about? Well, there are various ways of posing it, but that nothing is any better than Schrödinger's cat, in my opinion. Here's the classic case of quantum indeterminacy, if you like. And as Tim Maudlin and Jean Brickman have been stressing in the last couple of weeks at the last couple of meetings, Schrödinger himself really took the example as being a reductio of the completeness of quantum mechanics, that there had to be more to it, because really size doesn't come into it. The point is that tables and chairs and everything else around are made out of millions and billions and trillions of tiny little Schrödinger's cats, really, and that's what the problem is. So I've juxtaposed this old chestnut, this quote from Alfred North Whitehead, just because, yeah, it looks like an absolutely nonsensical idea that there could be such a thing as a Schrödinger cat, but I'm out to show that, well, actually, we can have a perfectly intelligible, give a perfectly intelligible account of what a Schrödinger cat could be. And I've also proposed this, oh yeah, just getting rid of something, this quote beside it, because I think this is quite impressive too, from Max Born's Nobel lecture. How does it come about then that great scientists such as Einstein, Schrödinger and de Broglie are nevertheless dissatisfied with the situation? Somewhere in our doctrine is hidden a concept unjustified by experience, which we must eliminate to open up the road. I'm hoping to show you that on the way to making Schrödinger's cat intelligible, we can discover just that concept which we need to eliminate. So, there are many roads to trying to make sense of quantum mechanics. They seem to be multiplying, and they run into each other and diverge, and how I've come to this problem is by a different pathway to Christian, and other people have very different approaches. So for me, a good point to start off is, how do we make sense of probability if a subject splits on making a measurement? Now, I should say that there are plenty of people who think of themselves as Everettians and who don't think subjects split. And I'll say something a bit about that later on. But Everett certainly did. Anyway, so here we are. Here's in his seminal 1957 paper, The Trajectory, note the scare quotes, of the memory configuration of an observer performing a sequence of measurements is thus not a linear sequence of memory configurations, but a branching tree with all possible outcomes existing simultaneously. He also wrote about the same time in an unpublished work, as an analogy, one can imagine an intelligent amoeba with a good memory. As time progresses, the amoeba is constantly splitting. Each time, the resulting amoebas have the same memories as the parent. And here's Tim Maudlin in 2014, right in his review of David Wallace's book. It's easy to state the problem of probability in the Everett theory. Probabilities are standardly attached to alternatives. And here, apparently, we have no alternatives. Both outcomes occur. So where are the alternatives? So, if quantum processes were stochastic, it would be plausible that squared amplitude is objective of probability. Well, I know people might disagree about that, and I would just say that on the face of it, if you've got a lump of radioactive material with a given half-life, it does rather seem that the half-life is an objective property of that lump of radioactive material. It's telling you the probability that a certain amount of it will decay in a certain amount of time. So one could contest that perhaps, and certainly you could contest it, but as it seems fairly plausible at first blush, so let's just go with it. And now imagine 6 zillion parallel stochastic universes, which might seem unphysical, but it's not really, because modern cosmology tells us that, as far as we know, space is infinite and could contain a countably infinite number of galaxies. And also that what we inhabit is a finite, what's called the observable universe, currently estimated to have a radius of about 46 billion light years, which is where the furthest galaxies we can see are in our absolute elsewhere. That's how far away they are in our absolute elsewhere. So we are causally cut off from all the rest. So there could quite easily be any number of similar regions as closely alike as you like. So we could have 6 zillion parallel universes in that sense, and imagine that they're all evolving stochastically, and imagine that we've got Alice's spin measurement. It's 1/3 probability it's going to be down, 2/3 probability it's going to be up. Just by the law of large numbers, we've got the measure of the subset, which shows down, and the measure of the subset that shows upwards are 1/3 and 2/3 respectively. So now we come to the key thought experiment. And so we'll take a little bit of time about this. This was the sort of centerpiece of this paper at the top. On the left, we've got the conventional interpretation of this setup. We've got an Alice in each one of these parallel universes. And each Alice believes that the apparatus will show either up and down. It has a linear trajectory. She believes that it's a stochastic process and that one or other outcome will occur. And of course, on that interpretation, it's true, because each Alice will either find herself on the left branch or on the right branch, which she doesn't know which in advance. She also believes that the objective probabilities are 1/3 and 2/3. That's, given that if you believe that processes are stochastic, then you believe that there are such things as objective probabilities, which we're just assuming as being reasonable. Now, over on the right-hand side is an alternative interpretation of this setup. Instead of having one Alice in each universe, we've got a single Alice whose mind in some sense spans all of them. And her apparatus in some sense spans all of them. And when she performs the experiment, there's one Alice observing down whose mind spans the subset where the down result comes out, and the other Alice whose mind spans the other subset where the result is up. So what she believes that the apparatus will show either up or down, it has a linear trajectory, is actually false, because for her, unbeknown to her, the apparatus will show both up and down, and it has a dendritic branching history. But at the same time, she believes that the objective probabilities are 1/3 and 2/3. And that's true because the measures of the subsets, where she would see one and the other, correspond. So, will this alternative interpretation of mind work? I call it the unitary interpretation of mind. Takes its inspiration from an absolutely seminal thought experiment by Hilary Putnam in a paper in 1975. First step is just to imagine that there's a twin Earth somewhere. It's just like Earth in every respect, okay? And we've got a subject faced with an apple. Each one is seeing an apple, one subject on each planet. Okay, that's the normal intuition. And here comes the argument which Hilary Putnam launched. It's had very many different sort of variations on the theme, but honestly, the original is just as good as any if one overlooks some sort of rather superficial shortcomings. Some substance S has hidden molecular constitution X. Now, so you might think, imagine for instance, there's some crystal on Earth which has molecular constitution X. And on twin Earth, we find in exactly the same places crystals which look exactly the same superficially. You can't tell the difference. I should say that the thought experiment is set in 1750 before anybody did chemical analysis. So that's why it's hidden. It's hidden in the sense that nobody has had access to molecular constitutions. But it's also hidden in another sense. So these crystals on twin Earth, which look the same and are in corresponding places and have all the same superficial properties, it has some different molecular constitution. Why? But it's also hidden in another respect, which is that obviously you have to suppose that the difference in the internal constitution of these crystals hasn't had any further knock-on effects to make any other differences between the two planets, which is implausible, but it's very much like the Schrödinger box, where the interior is causally isolated from the exterior. So we have a subject on Earth saying, I'm faced with, incidentally, I thought maybe a nice example of such crystal would be obsidian, because the thing is that Putnam, the original example is water, which is H2O, and sort of twin water, which is XYZ. It brings some superficial sort of objections, but they really are superficial. But if for the crystal, the point is water is something very familiar in our environment that we have lots to do with. So obsidian could be this crystal. I mean, that's something that humans and their forebears have had lots to do with for a very long time because it makes excellent sharp edges. So there we are. I'm faced with a sample of substance S, says the man on the left. And that's true, because what he's facing has got molecular constitution X. The man on the right is saying the same thing, but it's false, because it's not S, it's S star. So of course, the word for S, whether it's water or might be water or obsidian or whatever, it's just a homonym. He's not referring to the same thing. There's a difference in the representational content of what they're saying or what they're thinking. And that means that even though these two, a doppelganger, which are exactly isomorphic, their bodies are exactly isomorphic, they're entertaining different thoughts. So, and there's, that's semantic externalism. And Hilary Putnam famously said, cut the pie any way you like, meanings just ain't in the head. And that argument is still running and still convinces a lot of people, basically. So, the unitary interpretation of mind. The idea is now, instead of two subjects, we've got a single subject whose mind spans the two worlds. Well, that looks pretty weird, because these might be very, very far apart. How does this work? But actually, this is an exercise in what the philosopher Donald Davidson called radical interpretation. Imagine we've got a bird's eye view of these two planets, and we're looking at the goings on, and we're trying to impute meaning to understand the mentality of the creatures that are behaving in front of us. So instead of interpreting it as being two distinct doppelgangers with two distinct minds, can we interpret it as being a single mind spanning the two worlds, entertaining exactly the same thought? I'm faced with an apple, mass 100 grams. So for this to work, we've got to have this other subject, the unified subject, unitary subject, if you like, has got to be speaking truly. There has to be an object in his environment, which is an apple, and has a mass of 100 grams. Well, clearly that can't be the aggregate of the two apples, because for one thing, it's two apples, it's not one apple, and the total mass is 200 grams, not 100 grams. So what else could it be? Well, since the late 19th century, there's another type of object which has been on the metaphysician's shelf, if you like, and that's the set. And suppose we just hazard the idea that actually what this unitary subject is seeing is the set of the two apples. And the set of the two apples is itself an apple, and it has a mass of 100 grams because its mass is that which the elements have in common. So basically, the idea is that the relationship between a subject and their body is rather like the relationship between a novel and copies of the books. Multiply up the copies of the book as many times as you like, you've still got one novel. Though you need one copy to have the novel. If they've got no copies, there's no novel. Similar thing now, the unitary interpretation of mind is that the similar thing applies to minds. Multiply up the doppelgangers, you've just got one subject. But if you don't have one doppelganger, then you've got no subject. There is a difference, however, which is that printed ink on paper doesn't contain meaning. For it to induce meaning, there has to be a reader. So meanings aren't in the print on the page; they're in the head of the reader. And for the but for the subject, the idea of semantic internalism is that meanings actually are in the brain of the subject. A brain, of course, being a vastly, vastly more complicated thing than ink on paper. And so maybe the sort of thing which could indeed entertain meanings. So if we now apply this to Putnam's argument, of course, it just evaporates, because now we've only got one subject, and it says I'm faced with a sample of substance S, and that's simply false, because substance S has constitution X. What he's faced with is a sample with indefinite molecular constitution, because it's a set of samples with different molecular constitutions. So that blocks the argument for semantic internalism, opens the possibility of semantic internalism, that meanings may well be in the head after all. And as it happens, current theory in cognitive neuroscience, a favorite theory at the moment, is prediction error minimization, very much suggests the semantic internalist attitude. So there's a tension between current cognitive neuroscience and current philosophy of mind. So let's develop this a bit further. He's now faced with an apple which has a mass of about 100 grams. The idea is now there's just a slight difference between the apples. It's an imperceptible difference. So we've still got one subject with one apple in front of him. The aggregate has definite mass, 200 grams, but the set has indefinite mass, not less than 99 grams and not more than 101 grams. So that's shared property of the two apples. It's like quantum superposition. You can see the analogy. So the first immediate objection, is this what philosophers call a category mistake? This phrase comes from Gilbert Ryle in a book, The Concept of Mind, in 1949, and has come into general circulation. It's the idea, a category mistake is when you attribute properties to some object, and the object is just not the sort of object to have those sort of properties. That's the category. It's only a certain category of objects which can have those sort of properties. So for instance, an example which Ryle would be talking about would be, look, you can't talk about a brain thinking about tomorrow. People think about tomorrow, a person thinks about tomorrow, a person might have a brain, but you can't say that it's the brain which you're thinking about tomorrow. The idea is it's a category mistake. You can attribute thinking about tomorrow to a person, but you can't attribute it to a brain. So the category mistake here would seem to be that sets are necessarily abstract objects. The mathematical concept of a set is applicable to apples, but the set of two apples can't be an apple. Okay, so let's remember what Max Born said. Somewhere in our doctrine is hidden a concept unjustified by experience, which we must eliminate to open up the road. Is it unjustified by experience, this assumption that a set of apples can't be an apple? Well, it would seem that it's very much justified by experience on the face of it, because here we have two apples. You can't see the third one. So why not? Well, you can't see it because it has indefinite position, because the two apples are at different positions. You can't detect its mass because you can't interact with it. To do so, you'd need to have a body which was a set of two doppelganger. And to see how this works, look, here we have someone down at the bottom facing two apples. He's seeing two apples, total mass 200 grams. Put each apple in a rocket, send it up to twin planets, where we've got a unified mind spanning the two doppelgangers, and he sees one apple, a mass 100 grams. So it's he up at the top can see the third apple, and he down at the bottom can't see it. That's why we can't see the two apples. The third apple, I mean. Right. So if the unit interpretation of mind is correct, and there are two copies of our observable universe, then the apple that we see, the apple in front of us here and now, is a set of two isomorphic apples which have total mass twice that of our apple. That would be the implication. Right. Now, let's go back. Think again about the unitary mind who is faced with an apple about 100 grams, because there's a slight difference between the two. He takes out a measuring instrument, and what does he find? Ah, it's 101 grams, it's 99 grams. He splits, just like Alice. The reason being, of course, that each doppelganger gets different sensory input, which has knock-on effects in its brain, which results in different cognitive states. So now, I think we can formulate what I call quantum set theory. And we can formulate it exactly in terms of Schrödinger's cat. Schrödinger's cat is a set of live cats and dead ones. The subset of live cats is a live cat, and the subset of dead cats is a dead one. The measures of the live subset and the dead one are the absolute squares of the quantum amplitudes of a live cat and a dead one. The live cat being the subset of all the live cats, and the dead one being the subset of all the dead ones. A corollary of that is that the set of an ordinary everyday live cat and a dead one is a cat. It has indefinite vitality, but it isn't a quantum superposition. We could call it a classical superposition. So let's try and apply this to an electron rather than cats. Let's assume that it's a point particle. It is, as far as you know, but we'll take it to be a point particle. It exists, it's somewhere within our observable universe, but it doesn't have a definite position, and it doesn't have a definite momentum either. So the background here is a low resolution version of the Hubble ultra deep field photograph, which has to be one of the most wonderful things that humanity has ever managed to produce. The single electron in the observable universe is a set of elemental electrons, each with definite position and momentum. Each of its subsets is an electron. So we have a region over here, region A, which is a subset of elemental electrons, and the measure of that subset on the whole set is X, and region B has got measure Y, and that is squared amplitude for the squared amplitude position for that electron. A subset electron for a given region has elements with a range of momenta in accordance with the uncertainty relation. So the more you constrain the region, the less you constrain the momenta. That has to be so according to the uncertainty relation. So by way of illustration, suppose that there are minimal regions which are Planck volumes. Of course, we could imagine that space is infinitely divisible, but let's just to keep it simple, just to get a first grasp of what might be going on, let's think that there are minimal volumes. A single electron may have a position amplitude for every region of the observable universe. Imagine a free electron which has been sort of floating through space or zooming through space for a long time. So here we are, here's a Planck volume. It's got a load of elemental electrons in it. The subset electron for a Planck volume has elements with a maximally wide range of momenta, of course, because it's a minimal region. And an elemental electron is a local beable in just the same sense as the particles in pilot wave theory are local beables. And so we get 2 cheers from John Bell, because I think he wasn't too keen on many worlds theory. So that's why not 3 cheers. Here we have the classic two-slit experiment. The single electron passing through the left slit and the electron passing through the right slit are each a subset of the single electron propagating from source to screen. Many electrons in the same place at the same time, implying a novel non-spatiotemporal extension, environmental cardinality. So the idea is that the single object in an environment is constituted by a whole load of objects which you can sort of think of as sort of stacked up behind the one that you can see, if you like, in a sort of, to try and visualize it. But environmental cardinality will typically be a very large number. So the overview then is this. The electron in his environment is a set of elemental electrons, each in its own parallel universe, where these totality of parallel universes are now not being thought of as being stochastic parallel universes. It's rather that it's a whole load of parallel universes which in their entirety effectively are the concrete manifestation of the universal wave function. His mind spans that multitude of universes where elemental electrons have linear histories, having precise position and momentum. They, of course, have trajectories. So, parallel universes in Everettian theory, they've made several appearances. First appearance, I think, undoubted, well, and I'm sure that is right, it was in this paper, Quantum Theory as Universal Physical Theory by David Deutsch. And it was elaborated for the sort of for the general public in his book, The Fabric of Reality, which came out in the late 90s. And why did he introduce this? Well, the idea is that if you remember, going back to the Alice's, the idea is that each one thinks, going back to the Alice's on the left-hand side of that thought experiment, where there's one Alice in each universe. The idea is her apparatus is going to show one result or the other, but she doesn't know which. So she doesn't know which sort of universe she's in. And of course, David Deutsch isn't assuming that each universe is stochastic. That would be no point. That would undermine the whole purpose of what Everett was trying to do. It's rather, as I say, that the ensemble of the universes manifests the wave function. So although he didn't say so, it's implicit in David Deutsch's idea, this idea of self-location belief. It's the idea, self-location uncertainty. Alice is uncertain which of a number of different universes she's in. This idea about self-location belief, self-location uncertainty, was really sort of came to the fore in completely, again, separate from quantum theory by this paper in Adam Elgar in 2000, in Analysis in 2000, and it's been greatly discussed ever since, both in classical and quantum settings. Another introduction of parallel universes is in Simon Saunders' chapter in the Many Worlds book, and that is similar in some ways to David Deutsch's, but different too, and also is based on this idea of self-location uncertainty. Likewise, in David Wallace's book, in his chapter 7, he has a similar way of thinking about the uncertainty of an upcoming measurement. That's based on a paper which came out in 2008 in the British Journal for Philosophy of Science by Simon Saunders and David Wallace, A slightly different approach from the one in Many Worlds, the Many Worlds book. Over on the right, again, objective probability and Everettian quantum mechanics, that's Alistair Wilson, 2013. That basically picks up on Simon Saunders' idea and develops it into what's known as a sort of version of modal realism, something that was sort of made famous by the philosopher David Lewis. And Alistair Wilson has just, a book came out just a few months ago, which elaborates this idea. Down at the bottom are a couple of papers. There's plenty of propositions about parallel universes going on. Here are two quite different approaches. This one, the one at the bottom on the right, is quite unusual because each parallel universe is itself splitting. And the one on the left, which seems to me very interesting and might be getting a, I don't know, I mean, this is very speculative from my point of view, but perhaps it's getting a better hold on what the nature of this, these multiple parallel universes is. This is in a recent paper by Kai Weigel and Kelvin McQueen. So, takeaway message. Whoops. Take a set of parallel universes and add unitary minds to yield many worlds with indefinite environmental objects constituted by sets of local variables with linear histories and definite environmental objects with dendritic histories, like Alice's body and her apparatus. So now, how do we include spin and entanglement and all the rest of quantum theory? Well, a moment's thought tells you that it's going to get very complicated very quickly. And I only got as far as thinking about really completing what I've said to you so far only a matter of a couple of months ago. So it makes my head spin trying to think about spin and entanglement. So it's quite possible that this will all come to grief. It's impossible to extend it, and the house of cards collapses. But if that's not the case, then it does look that a road is open up for us. If we eliminate the concept, unjustified by experience, that a set of two apples can't itself be an apple. And there we are. Thank you.
Thank you. That was cool, as far as I'm concerned. So, as I was saying earlier, if people that have to leave earlier want to give a first comment or want to ask questions, let me know. Otherwise, we can start. Okay, we can start directly with the audience then. Okay, I see David.
Yep.
Yeah, you can go.
Just, well, a technical point really. In ordinary set theory, a set can't have multiple identical elements. So this would have to be something, I think they call it a multi-set or something. And even then it's not enough because it doesn't, it has to have a the elements have to have a weight or something. There's a continuum involved. When you say set, do you mean an enhanced object like that?
No, I don't think so. I mean, when you say a set of identical objects, I mean, you're saying you can't have a set of qualitatively identical objects.
Yes, in normal set theory.
Right.
It's only a technical
well, I think that would be because mathematically, you can't have numerically distinct and qualitatively identical objects. Wouldn't it? I think that would be it, wouldn't it? So,
well, some philosophers say you can't, but mathematics allows you to. You can just attach a number to each element of a set to make it a multiset, or you could attach a real number for each object, and that would be like the weight of how many of those.
Right. Okay. It does sound as if you're sort of attaching something to each element, which makes each element different, though. I think the thing is that to take set theory out of the domain of mathematics and bring it into the domain of physics, if you like, brings, it's a different type of object which are constituting the elements. So
It's not necessarily physical. I think they do this with, for example, if you want to talk about sets of roots of equations,
right.
when they're coincident roots, it can no longer be represented conveniently as a set of roots. You would rather have a thing that takes account of the fact that there's such a thing as a coincident root.
Okay. Well, all I can say that is fair enough. I can see how that would make sense in mathematics, but if we're starting to talk about sets of physical objects and proposing that they can themselves be physical objects, then it seems to me that we're in a different domain. I mean, so that what you're saying might not necessarily apply there, but you know.
Yes. Yep.
Yeah. Okay.
Next one is Simon.
Yeah. Hi, Christian.
Hi.
Thanks for putting on this series and allowing me to attend. And Paul, thanks for a great talk. I mean, I mean, you and I have talked about these things many times, and I'm slightly concerned that there are aspects of your idea that others haven't understood properly. But rather than, I mean, here's a way of framing it. In a universe without any people, presumably your central idea would still be applicable. Can you just tell me yes or no on that one?
Oh yes, absolutely. Yeah.
Right, good. So it's a generic proposal for how to talk about reality, if you like, or how to comprehend reality, that is supposed to elucidate what's happening in quantum mechanics and specifically the Everettian interpretation. But my question is that, and I'm sure you're aware of it, and I just like comment, and I wonder if other people understand this rightly. It's not that you're supposing we should, as it were, rewrite quantum mechanics using set theoretic notions, right?
No.
Right. So physics still sort of goes on as usual.
Absolutely, yeah.
Right. But then, I mean, and I think it perhaps makes it more vivid if we stick at the microscopic level. So you've got the physical description of the microscopic level in terms of the quantum state. Somehow in parallel to that, there's another description going on in terms of your idea of unitary sets. And it's very unclear to me how those two types of descriptions are supposed to...
Oh, right, okay. I understand what you're saying. Okay, look, the point is this. It's all about how the environment of a subject is determined. The idea is that what we're dealing with in our environment is objects of our environment, and the way that we're trying to explain indefiniteness is that indefinite objects in our environment are sets of these elemental objects which are not in our environment. Our environment is composed of them, and the point is, yeah, take away subjects, all you've got is all these sort of parallel universes, if you like. But as soon as you introduce a subject, then the subjects, that subject, I mean, something that can have cognitive states, then that will span these a set of universes in the way that I explained. And so the object and environment in the environment of that subject will be composed of sets of these sort of elemental objects. But you're right. I mean, if you take subjects away, all you've got is just the elemental objects. It's only that when you introduce subjects, what constitutes their environment are not these elemental objects. They're not situated in a single universe. They are necessarily situated over a multitude of them. So the objects in the environment get to be constituted differently. Does that make sense?
Well, somewhat. I mean, but you sort of said yes and then you said no. So I was asking you, does there have to be a subject present, or does the analysis in terms of unitary sets and so forth apply even in a universe without any people and so forth? And you said yes.
Well,
but now
well, yeah, but it does. I mean, it does. I mean, the point is, I mean, you imagine sort of looking on all this multiplicity from the outside, if you like. There are no subjects in there. Then, of course, yes, that a set of these elemental objects would constitute an object, and if there were a subject around, then that would constitute an object in the environment of that subject. But it would, yeah. I think that's as much as I can say, really.
Well, okay. Let me not push you on that one then, but let's just, the further thought then, these elemental objects. So they're well defined even in the absence of subjects, right?
Yeah.
Right, and yet they're point-like with point-like positions and momenta, Bohmian particles. So now there seems to be a sort of a quantum mechanics as we know it and love it, and then the quantum mechanics with point-like particles that some of us love, and we all know. You know. But, so my question in a way is, how does the quantum mechanical usual description of mathematics and so forth sit side by side with these collections of point-like entities?
Well, quite simply that the objects in, let's say, the laboratory of a quantum physicist when it's dealing with some sort of superposition, the idea is that object, what that object is a set of these elemental objects. And so, as you said at the beginning, it's not aiming to change the physics in any way. I mean, it is, the idea is to supply a metaphysics which is able to tell you how you can have such things as Schrödinger cats or objects of superposition in the environment. You can have them how can you have them and have local beables? Well, that's what I've been trying to, suggest how you could do that. So the physicist is dealing with these objects and using whatever techniques he uses, and in a sense, he or she, I shouldn't be saying it, in a sense, that's fine, and in a way that's a sort of, you can do the physics without the metaphysics. The metaphysics, you leave it in brackets, and it's a mystery, or it's the problem. But what we need, I think, that's what we need to sort of to resolve the perplexity about quantum mechanics, is to have a metaphysics which is suitable.
Well, okay, just last quick question. Would you call your theory, would you call it a hidden variable theory?
I don't think so, no.
Okay, but a sort of a metaphysical equivalent of a hidden variable. Fair comment.
Simon, I think the thing is, we're talking about sort of EPR and that sort of stuff. I think if you've got the sort of the Fission view of many worlds, then you don't have EPR non-locality. I think that's You know, but I mean, let's not go into that now. But,
no, thank you. I've asked. Thank you.
Yeah.
And thank you, Simon, for the comments. So now the list reads, Baptiste is the following, then Jeremy, then Jan, then Aurélien, and then Lev. So if I forgot someone, please let me know. So Baptiste, you're next.
Hi, thank you very much. I have a question about the notion of set. I would like to know whether it's an essential aspect of your view, or whether you could use instead a notion of merological sum, right? Thinking of objects as having different parts in different branches. The thought being that you could avoid the claim that apples are abstract objects that you can see, right? Because the notion of merological sum and parts are more friendly to concrete objects. So have you thought about that?
Yeah, do you know David Lewis's book, Parts of Classes?
Yes.
Yeah. So basically the, you know, I have to bring this up from the back of my mind, but I do actually mention this in that, that 2017 paper. The proposition is at odds with his main thesis. I mean, he tries to do set theory in terms of mereology, and this is actually contradicting his main thesis there. So I don't think you can do it in terms of mereology, to be honest. I mean, if you've got the two apples, right? The mereology gives you each apple as a part of the pear, and then it gives you, you know, pips and peel as parts of each apple, and that. But I don't think it's going to yield this third apple. At least I can't. Do you see how it's going to yield the third apple? I mean, the point is, we've got to have, if the whole thing rests on this idea that we can do this unitary interpretation of mind. So we have to have an object out there. I don't see how you can have an object out there mereologically, but you know, I might be wrong. I don't know.
I mean, it's just that I was a bit. Did the notion of aggregate in your talk?
Yeah.
Was it synonymous to merological sum, or was it different?
Yeah, absolutely, yeah.
Because you said something like an aggregate of two apples, one being each with a mass of 100 grams, should be 200 grams.
Yeah.
But it doesn't seem to be the case in the with the traditional notion, at least in the philosophy of time, right? Think of an apple being made of two temporal parts, each being 100 grams. We would not say that the apple mass
that's good.
is 200 grams for this reason.
Good,
so,
good.
Yeah.
Okay. A mereological sum of temporal parts. Yeah, right. I see what you mean. So you're saying, by analogy with that, you could think of the parts for the unified subject being related like temporal parts. Yeah. How can I put this? I mean, the thing is, I mean, I haven't talked about this at all today, but another part of making sense of the splitting idea, of Alice splitting, is that you need to have some theory of transtemporal identity, which to work out, you know, what's going on, because Alice up and Alice down apparently are two different people. How can any one of them be identical to Alice? And I've specifically several times I've written about this. What we want for that is Sider's stage theory. Yeah, so you take So you take an object to be an instantaneous state. Are you familiar with stage?
Yes.
Yeah, right. So there, in stage theory, then an apple is the momentary, the temporal part. So you would not. How would you go? I mean, if you had this apple today and another apple in the future, which is a future temporal counterpart, then you would take, what you're saying is you take the mereological sum of those two, and that would still have a mass of 100 grams. Yeah, right. Yeah.
I mean, at least we will not say that there is a threat of us ascribing to the stage the property of having 200 grams. But I guess even if we have another sort of four-dimensionalism, the more perdurantist one, we will not do. I guess we will be fine. But I mean, it's. I don't know. I mean, I don't really have more to say, but it's just I thought that maybe the notion of part will not be that bad for your project. But yeah, I don't know.
Right, fair enough. I mean, yeah, needs to be sort of laid out what the relationship is, yeah, to mereology. Yeah.
Thanks a lot.
Thanks.
Jeremy, you up next.
Thanks, Christian and Paul. Thanks very much for this talk.
Jeremy, yeah.
There's a lot of interesting things there that I would want to follow up on, but I'll restrict myself to just one for now. So, and this is actually just coming out of the conversation you were just having with Baptiste. So you were mentioning that you would like to invoke Seiderian stage theory here. If I'm recalling correctly, in your earlier work, you know that like on one pass, Seiderian stage theory leads to post-measurement, pre-observation uncertainty, or uncertainty. The usual stochastic sense of uncertainty is recovered in this sense, or can be recovered in this sense. So basically, I'm wondering how to square that with. I was under the impression that the current view that you're talking about is meant to preserve something of the spirit of Everett's skeptical intuition. As you were saying today, no, there are no alternatives. Yet right. on this one application of the stage theory, though, we do get the alternatives. So, yeah, if you could help me square that, or how that's meant to play.
Well, so on the stage theory, I mean, Alice will be Alice up, Alice will be Alice down. It's not a question of that she will in fact be one or the other. She bears the relationship will be to each of them. Still seems to me there are no alternatives there. I mean, she will. I mean, in my last synthesis paper, I was arguing that you can understand pre-measurement uncertainty in those terms because, well, I don't want to get too far away now, but I mean, if you're identifying branch weight with objective probability, then the uncertainty comes from the fact that you are assigning different degrees of belief to different outcomes, but even if they're simultaneous, if they all exist, you're still applying uncertainty. The cognitive state of being uncertain is applying multiple less than one degrees of belief in different outcomes. And I'd argue that you can be doing that when you're distributing them across coexistent outcomes or alternative outcomes. But to get back to your question, I'm not quite sure. You were saying sort of your alternatives still arise. I mean, I think, yeah, perhaps I'm not quite understanding it, because certainly the view I'm taking, and I think that Everett took, was that there are no alternatives. Nothing. It all happens, sort of thing. Sorry, am I going off track a bit?
No, I think yeah. So I mean, just to restate the tension that I'm currently experiencing. So after measurement on the stage view, we have Alice in a state of ignorance between whether she is the stage with spin down or the stage with spin up. Right. Yeah.
Well, actually, the thing is, this is the point I was trying to make in that last synthesis paper, that actually we don't need to have recourse to this post-measurement pre-observation uncertainty. I mean, and in fact, the picture actually, with the unitary interpretation of mind, the picture changes actually, because imagine Alice is blindfold. She does the measurement, then, and this is what I argued in the 2017 paper. If she's blindfold, then her apparatus is in macroscopic superposition in her environment, because she doesn't split until there's a cognitive change. For the subject to split, there has to be a cognitive change. So a single subject will, if you like, span two doppelganger to the extent that those doppelganger don't differ enough to cause a cognitive change. So we could imagine there are little differences in the doppelganger, because they're having tiny little influences from the different outcomes on the apparatus. But until there is enough influence on her to actually cause a difference in cognitive content in the two doppelganger, and then she won't split. So in that paper, what I talk about is, you can imagine she's blindfolded, and then she does the experiment, and then she's got this superposition, the apparatus is in superposition in her environment, and then you sort of ring a bell on one arm and blow a whistle on the other arm, and she doesn't know whether the bell goes with up or the whistle goes with up. So then she can be uncertain about which branch she's on. So you can recover that. But in that paper, I still thought it was important, but I now think that actually we can recover pre-measurement uncertainty, even in terms of splitting. But that's what I tried to argue anyway. That's what's in that synthesis paper. But which doesn't mean to say that post measurement pre-observation uncertainty doesn't have a role. I mean, it does in everyday. We know that if you just in an ordinary situation, you roll some dice and you've got a cup over the dice, you're in exactly the same situation as before you roll the dice, really. So, in fact, really, what I'm arguing for now is that there's total symmetry. We don't have to appeal particularly to the post-measurement situation to regain uncertainty, but then that's going away from what I was talking about today, really. Yeah.
Yeah. So sorry, I won't pursue this too much further. But where I'm at is I understand how, if we're just looking at an agent who we define that after the splitting, right? The agent is all of those stages. The agent spans
Yeah.
all of those stages.
Right.
I understand how we could have objective probability by just referring to the parts of that agent. But I don't understand how we could have uncertainty.
Right. Well, I mean, I did write it down in, I think it was section 2.3 of that synthèse paper, and I don't want to try and paraphrase it. So yeah, because I think I'll get lost. I think it's quite difficult to articulate because it's so counterintuitive, but I think it can be done. Yeah.
Great.
Okay,
yeah,
but
thank you.
Yeah.
Jean, you're up next. You might be mute.
Yeah.
Something that happens. Yeah. Now I can hear you.
Okay. Hello. Well, I have a simple question. I mean, because I don't understand very much about this philosophy, semantics and so on. Do you have local variables or not in your theory? In the sense, because I always hear you speak cat and so on, and people and everything. I mean, these people are located in three-dimensional space, right?
Yeah.
Not functions. Wave function is just a function. It's defined in space.
Well,
as the bird, it's hard to have a function defined on configuration space when there are no configurations. And here my problem is that you are talking always as if there were things in three space or four space if you include time. And you see what I mean? I mean, there's this big gap in many ways.
Right.
On one hand, you would like to say, oh, it's all the wave function, nothing else. And then there are things in space like cats and weights and masses and God knows what.
So look, the idea is that yes, there are local variables, and they're absolutely everywhere. So the idea is that in fact, this is a sort of concrete manifestation of the wave function. So if we can imagine going back to this, we've got the wave function of this single electron, and imagine it's got some position amplitude everywhere in different regions. Different regions will have different subsets of these elemental electrons. So there will be the whole of space is full up with elements of this one particle. And if you've got lots of particles entangled in space, then every particle will have elements at every position. So it's
so you're saying that there are actually fractions of electrons all over the place.
No, they're not fractions. They're elements. I mean, it's the idea is, as you know, you go right back to the apple, because the point is, I mean, bizarre as it may sound, the idea is that if you've got two apples, there really is a third apple there, and it has each of those apples as elements, and the same goes for the electron. There is that one electron is the set of all these vast multitude of elemental electrons, and each one of those elemental electrons has the mass of an electron.
What am I supposed to be? Are there
What are you supposed to be? What you're supposed to be is you're made up of a vast number of particles, each of which is in superposition. You'll be made up, or every point in space in your body will be full of these elemental particles. There'll be loads and loads of them at every point in space, and they will have definite position, definite momentum. So there will be local variables in exactly the same sense as the ones you want in pilot wave theory.
Yeah, but then what's the difference? I mean, am I myself located in many different places at the same time? I'm just trying to understand.
Yeah. Well, okay, fair enough. Well, look, I mean, it does mean that we do have to change our understanding of what it means to be located in space, because going back to the idea, you know, we live within a finite observable universe, which is causally isolated from all the rest. And there could well be multiple instances of that. So even without talking about the quantum mechanics, that means that on the unitary mind idea, what I take to be a position in space is actually a set of positions in what I used to call space. I mean,
I'm not located.
I mean, that would be, I mean, I think that's intelligible. Sorry, yeah?
So I'm not located where I think I am now in my bed, but I'm not located.
Well, yes, you're located, but your location is a set of locations. A set of locations is a location. How could I put it? You see, I mean, it's going back to this really early on. Which one was it? No, it was a bit further back. Hold on, I'm good. I mean, well, I don't know which one I'm trying. Where is it? Further, it's further up or further down. Hold on. Oh, I know. I think it came after that, didn't it? Yeah, here we are. Here we are. I mean, the thing is, you know, this really requires a radical change of perspective. I mean, normally, if I say here I am located, and there's a twin Earth somewhere, you know, zillions of light years away, with a doppelganger of me on it, well, then that's another person located in another planet. Here I am here, and they're over there, sort of thing. But if the unitary interpretive mind is correct, then they're both, where I am is the set of those two locations.
Okay.
Yeah. So these at the top there, these two, they're meant to be two sort of causally isolated observable universes, which are twinned, if you like, and they've got an apple in them. And the apple in my environment is the set of those two apples. So the location of that apple in my environment is the set of the two locations of those two apples at the top. I know it's very counterintuitive, but I don't think, does that help?
Well, I can understand the thing that there could be a doppelganger or whatever, but is that what is happening all the time? Each time there is a quantum experiment, sometime in the universe, with several possible results, and there are doppelganger of me proliferating like that, and they're...
Well, I mean, I don't think that's necessary, but I mean, there's an interesting sort of link between the idea. I mean, what I've just been talking about, it would go, supposing space is finite, you know, supposing there are only 10 trillion galaxies and we're just sort of living in a little bubble of 200 billion or something. All that I've said would still work. But if space really is infinite or very, very big, enough to contain multiple copies of our local universe, then there's a sort of an interesting interplay, if you like, between how we're situated in that spatial multiverse and how we're situated in this quantum universe. The two sort of have got some sort of interesting relationship with each other. There we are. I don't think I can do any better than that at the moment. But I mean, I'm fully aware that what I'm proposing is highly counterintuitive, and it's quite difficult to grasp sometimes. Which is probably why I've had such a lot of trouble trying to get it out there. But I do think I think it can be. It is coherent, but still difficult, perhaps conceptually. Yeah.
There's a finger from Lev, I think. We have time enough, but yeah, you can go. Lev.
In fact, my finger was on Jan's comment because it was similar to what Jan said in Harvard lecture, and that he needs be able to describe himself or any anthropomorphic object. And you agreed, and I was kind of upset because in many words, you definitely don't need any beables. And Jan is a wave function in three-dimensional space. So it's perfectly understandable in one word what the Jan is. Especially if there is a collapsed wave function, then there is no problem whatsoever. The collapsed wave function of Jan is in 3 dimensions. So no problem whatsoever. Of course, when Jan in the superposition of being here in the next room, and you still think that this is Jan, this is, of course, I think not understandable. When the electron is a set of 2 electrons, this is, I think, not understandable. It's kind of, but this is the issue beyond it.
Okay, well, look, just to pick up on the last point first and then go back to the first point. I mean, is the idea that a set of 2 apples is an apple, is that understandable?
I think no.
Okay. Well, fair enough. Right?
I would say if I teach set theory, I will my student will not pass the exam because it doesn't. So I don't understand what it is.
Well, okay. So if you don't, then I mean, if you don't take the argument as it applies to the apples, then of course you won't take it as applying to the electrons. I agree, but so remember that the argument for the apples depends on this slide, right? That the idea is that you can't see the person down at the bottom. You can't see the 3rd apple, but if I send the 2 apples up to the twin planets and there's a person whose mind spans the 2 planets, then they can see the 3rd apple. But I don't want to. I mean, fair enough if you don't find that intelligible, fair enough. But the other thing is, I know that you've got another argument for local variables. I know, what you were saying before about the center of mass and so on. I know you have this argument. But look, it's not accepted by everyone. For instance, Tim Maudlin doesn't accept that argument. So all I can say is that I'm suggesting that there's a different way of having local variables in many worlds theory from the way you're suggesting. And some people find the way you're suggesting inadequate, but that's a big argument sort of thing. I mean, I think that's an argument which has been going on for some years between many worlders and opponents such as Tim Maudlin. Yeah.
Just it was a finger, so I cannot continue. But what I understand, Everett wanted to not to add anything else, and Bell wanted to add local variables. So in the moment you put local variables in Everett, it's not Everett anymore.
Well, I'm not sure that's right, because I mean, the thing is, as I understand it, you see, if you've got the local variables in the in pilot wave, then there's extra physics is required, and there are problems with relativity and so on. But the way that I've introduced local variables to Everettian theory, I don't think it creates any sort of problems for physics whatsoever. It's entirely a matter of metaphysics. So I don't see how similar sort of problems could arise. But the thing is, look, Everett couldn't have got it all completely right at the beginning, because otherwise we wouldn't have been talking about it for the last 60-some years. So the thing is, what I would say is the point is about Everett, the physics remains untouched, and I think and I agree with that, and I think that I have not touched the physics at all. All I've done is added some metaphysics to help to make sense of it, to help to make sense of such things as Schrodinger's cat, and yeah. So I don't think I've added to the physics. So in that sense, I think it's right to call it Everettian, but it is, however, adding something. But it's entirely in the domain of metaphysics, I think.
We could come back to this if we have some time. I would like to as well. So
yeah,
for once I would go against my duties maybe. But first I have Aurélien, and then Chip, and then Lev, who maybe has a question. So Aurélien first.
Okay. So thank you, Paul Tappenden, for this very interesting talk. This Everett theory is very fascinating. From what I understand from this discussion, is one of the problems is the ontology. This is probably the question raised by Jean about the meaning of the wave function in this theory. Okay, this is an issue, but what is more interesting me is the problem of the probability that you mentioned, because this is a very old problem, as we know, and the issue about the probability meaning in this theory is very peculiar, because there is a lot of debate about if we are really right to discuss about probability in the Everett interpretation. In this seminar, we have different people working on this topic, so it's very interesting to have this occasion to have maybe their opinion. But if the feeling that your picture is something related to the whole debate about the many-mind interpretations of Albert on one side, David Albert on one side, maybe Michael Lockwood on the other side, and where one part was stochastic and the second interpretation was let's say unitary and deterministic, and I have the feeling that it's something related to that, but I'm not really sure, because in the Albert point of view, this is like a Bohmian picture in my way of thinking. It's a Bohmian picture in which the mind is surfing on the wave and is stochastically driven by some amplitude. But on the interpretation that which will be completely unitary. As you show in your picture, you have Alice, which is split into two branches, one maybe with no square amplitude 1/3 and 1/2. I don't remember exactly what was exactly on the
yeah.
And I don't really understand for you if there is a kind of you need to, yes, this picture. I don't know if you need to have some kind of stability of the mind which is preserving during the time, or if you really believe that you have two Alice, or if you have many Alices, and if that case, if it is closer from the Albert point of view, or maybe from the Lockwood point of view.
Well, I think it is. It's very different from the Albert and both Albert and Lockwood, I think. I mean, because the Albert and Lower is sort of stochastically evolving mind, as I remember it, and here there's no hint of that at all. I mean, I know. I mean, in this example, of course, where we were starting off, the idea is that these are stochastic parallel universes, but then the idea is at the end is to replace the stochastic parallel universes by a set of parallel universes which instantiate the wave function. So there's no stochasticity at the level of mind. The mind, it's simply a question of the fissioning of what's known in philosophy as personal fission, something which has been discussed. Maybe you know about that. I mean, the problem of personal fission was discussed quite a lot in the 70s and 80s, quite outside of quantum mechanics. Relating to the Lockwood, well, it's different from Lockwood but something that I liked in Lockwood, and it was an idea which I think he attributes to David Deutsch, in fact, is this idea of what he called a Pickwickian superpositional dimension. It's this idea that there's some sort of non-spatio-temporal extension to the world. And on the view that I've sort of presented here, that's captured in this idea of what are called environmental cardinality. So how can I put it? I mean, the way I've got to that idea is by the idea of the single mind spanning a whole load of doppelgangers. Whoops, just knocked down the water. A whole load of doppelganger, each one in a different universe. That's different from the way that Michael Lockwood was thinking about it. But I don't think I can say any more on the relation between that and those theories, except that, I mean, I think the idea that the problems for quantum mechanics have got something to do with how we understand mentality, have had various manifestations, obviously, throughout the years, and is seen by some as maybe essential, seen by others as no, completely the wrong way to go about it. Mind shouldn't come into it at all. I just think that I've tried to introduce issues and an issue in the philosophy of mind in quite a different way than it has ever been introduced before, to trying to understand quantum theory, and which, as it happens, also has great important implications for theory of mind, because, I mean, in Anglophone philosophy of mind, this semantic externalism is very much the majority view. And so what I've done, I think, is to make a link between a very fundamental debate in philosophy of mind with very fundamental debate in philosophy of quantum theory, which is, you know, can there be such things as Schrödinger cats, for instance? Can there be such things as metaphysically vague objects in that sense? So, yeah, I mean, I can't do a very enlightening sort of comparison with previous views on mind. I'm a bit sort of quite fairly in the distant past in terms of my familiarity with them. Would you like me to say more about that? I mean,
Oh, I think okay. I understand. The point is that you have to add something in the Everett original theory in order to define something like a probability.
Yeah.
you have different strategy for that, and I'm believing that they're all. If you add something to the Everett theory,
right? Well, I think. I mean, look. I mean, let me just scroll down to it. Scroll up to it. Here. See this? The paper there. Bottom left. The paper bottom left. That was published online by Synthèse about a year ago. And what I'm exactly proposing is that what, Everett talked about it being a theory of pure wave mechanics, right? You drop the the collapse postulate. Well, I'm saying in that paper, I'm saying specifically, you drop the collapse postulate, but you have to replace it by a no collapse probability postulate. And that no collapse probability postulate is exactly just to say that branch rate, squared amplitude of branch, just is objective probability. That's what objective probability is out there in the world. Something, again, a first reaction to that might be a category error. I mean, how can objective probability be that? It seems something quite different from what probability ought to be. And yet, if there is such a thing as objective probability, it's pretty damn mysterious, and we shouldn't. I would say that we can't presume anything about what we have traditionally thought of as probability in saying what it must be. I mean, I'm saying, well, objective probability just could be branch rate. That's what it is. And counterintuitive as that may be, if we accept that as a hypothesis, then it works. I mean, because if branch rate is objective probability, then if I'm making a measurement and I know that the branch rates are going to be 1/3 and 2/3, then they're objective probabilities of the outcomes, and I'm going to assign a degree of belief of 1/3 to one outcome, 2/3 to the other, on the presumption of principal, Lewis's presuming that, which of course up until now everybody does presume, has always presumed. Certainly people can talk about justifying the principle, but that's another issue. But if I accept the principle, then if I accept that the branch rates just are objective probabilities, then there really isn't any problem. I assign my subjective expectations what I like and align with them. And I would say that if I've got stage theory to explain personal fission, then and put those together, then I can make give an intelligible account of Everett's idea that you split when you do a quantum measurement like that.
Okay, that's it.
Yeah.
It's a bit difficult topic. I have to go back to the.
It's a difficult. I mean, I don't know if it's going to be possible. It was. I know probably it's not going to possibly it won't be possible. But if there is going to be a session to talk more about it next week, we'll have some time to think about it, because I know it's quite a lot to digest.
Okay. Yeah. Thank you. Thank you very much.
Okay.
If not, next one is in 3 weeks. So anyway, we will.
Oh, okay, right.
We'll have a free discussion on your and left talk if next week we can't meet.
Yeah.
So that was my idea. We always have an anarchic discussion after the talk. So
well, I think it's a good idea to have time to think about things and let them sink in before. Yeah.
So next one is Chip. Finally, thank you for waiting.
Hi. So in your response to both Simon and Lev, you were saying that all you're doing here is metaphysics.
Yeah.
You're not changing the physics. And I push you on that, because when you say that you introduce these point elemental electrons, it seems like we're going to then need dynamics for those electrons. And if we're going to have some sort of dynamics from those electrons, some sort of law about how the electrons move, the elemental electrons, that's additional physics. So do you think that those electrons actually do follow definite trajectories? And if so, do you think we need a law to say what trajectories they follow?
Well, okay, good. I know, I mean, you've got some stuff on Newtonian many worlds, haven't you? Which seems might be sort of relevant here, but to me it seems, and I say it's only fairly recently that I've come to the point of thinking that you have to have these elemental electrons, but and so I haven't had a lot of time thinking about it, but it sort of superficially, it seems to me that their behavior should derive from the behavior of the wave function somehow. I mean, it should be implicit in how the wave function evolves, how their trajectories evolve, if you like. But honestly, I can't say more than that. But I mean, if you're right, then you do, and you do new physics, then it does seem like you're getting away from what Everett intended, absolutely. So honestly, I can't say more than that. I mean, it's certainly something I have to think about seriously, yeah. But for you, I mean, from your point of view, you think you would have to have some supplementary physics, you'd have to have another layer of physics to deal with that, do you think?
Yeah, I think you would. I think you'd want some kind of dynamics for how those particles evolve, an equation. You can derive some things from the wave function about how that equation should look, especially if you have ideas about maybe the density of these electrons, and you want to have some sort of flow that conserves the density in the right sort of way. That'll put some constraints on the kind of dynamics. You might end up with Bohmian trajectories for what these particles do. But even in Bohmian mechanics, those Bohmian velocities are not uniquely determined by having the density flow in the right way. There are actually other possible guidance equations for the particles that have the right flow of probability or density. So it's still an extra postulate. So I think here there's going to have to be some extra specified dynamics if you want definite trajectories for the electrons. Otherwise, you might say something about, there's no facts of the matter about identity of electrons over time or something like that might get you out of it. But if you're going to have real elemental electrons following paths, I think you're going to have equations for that.
Do you know that paper a few years ago by Gelman and Hartle about, what was it, some sort of title about, it was like a one world version of decoherent histories. I mean, I can't, I mean, well, I'll have to think about it and find it and send it to you in an email. But okay, well, look, fair enough. Yeah, perhaps you're right. But at the same time, what I'm thinking is, look, the wave function is telling you. I mean, when you talk about the density. Yeah, we've got a region with a certain measure of elemental electrons, another region with a different measure on the subset. I mean, that is effectively the sort of manifestation of the wave function. So if the wave function is evolving, it's telling you how those densities, in scare quotes, are sort of changing. So so again, it seems to me that maybe, but I mean, I'm absolutely not sure at all, that maybe somehow the dynamics is already in there, because the wave function tells you exactly what's going to happen somehow.
Yeah, I mean, just to illustrate the point about uniqueness that I was getting at before, that it won't tell you the exact dynamics, you could think just about the hydrogen atom. where you'll have a cloud of density around the nucleus. And you could imagine that it has that cloud of density because all the elemental electrons are staying put and there's more elemental electrons near the center. Or it could be because all of the elemental electrons are orbiting the nucleus in such a way that the density doesn't change. And so just knowing about the density doesn't tell you then about the dynamics uniquely.
Good point. I take your point. Absolutely. Need to think about it. Definitely.
Cool.
Good. Thanks. Nice to see you. Thanks for making the effort.
Happy.
Lev?
There is one thing which sounds very similar to what I'm saying, but the language sounds for me, which is from my point of view is strange. I say that if I have two branches and two aliases in two different places, and I don't want it to have it one alias, but I do accept that we need this weight. I put the weight as a probability to be found at this self-location. Now, and it's and you also wrote me a couple of times that you say that you have exactly the same position, but you say that this is objective probability. Now, the word objective, I don't know, there are metaphysics, I don't know what metaphysics is. What's physics, I think maybe roughly I understand. So about the word objective, I need operational meaning. Even it's Gedanken operational meaning. So let's assume there is a super intelligence, super technology which can observe the wave function of everything, and if there are every kind of variables and everything. So there is some external issue which look on our universe. And then you say that there are some objective probabilities of your kind. Can this universe will find out that they, according to the Born weight? Because what I believe that it might be that there is a subjective probability of a different kind. That we have unitary evolution, we have everything, the standard wave function, but we have a different log that, for example, that when I am in a particular branch and I don't know which one, and I know that there are several options, then the probability to be in each branch is equal, independent of the weight. And I think it's completely consistent. It's inconsistent with what we experience in our world, but maybe in some other world in which still the quantum mechanics, the wave function, Schrödinger equation is correct. But this probability self-location is different. The question, if it is objective and not subjective, as I say, then this external device, which has super intelligence and can do everything, can distinguish. In my case, external device which can observe everything, superposition, entanglement, Wigner friends, everything, cannot distinguish between my subjective probability. Can it distinguish from your objective probability? I'm not sure that this was, now it's very late and maybe I had more time to explain my question. But,
okay. I'm not, so what you're saying is that there could be a sort of possible world, if you like, where instead of assigning my post-measurement, pre-observation subjective probabilities according to branch weight, I just did it according to an indifference principle. And that, yeah. Well, I mean, I just don't know. Is that a possible world? I don't know. how can I put it? Sorry, yeah.
So it is possible. Can you distinguish it? If it's objective, then you say it can be distinguished. These two options can be.
Yeah, you would be able to sing it. Well, I mean, I mean, the indifferent. It seems difficult. I mean, in this world where the indifference option was prevalent, then there would be no quantum mechanics or something. I mean,
no.
I mean,
the Schrödinger equation is still absolutely correct. Everything is correct.
Okay, so but the observers, the subjects, would be getting things terribly wrong all the time.
No, only probability will be wrong.
Well, that's a pretty big thing, isn't it? Because they do an experiment and they have
probability is set location. You don't change anything. This is, you still have universal wave function evolved according to the normal equation. It just
right.
Inside have different statistics. They can send
okay.
but the super technology cannot use it.
All right, so they're in a quantum mechanical world, but they're getting what we would think of as very improbable statistics, which go along with the indifference principle.
For example, yes.
Yes, I see what you mean. Well, I think, I mean, if you're thinking about your omnipotent being, then they would have to be able to sort of see the cognitive states of the observers, wouldn't they?
You see the wave function. This is what you see.
You see the wave, yeah, you'd see the wave function, but I mean, is the omnipotent observer, are they able to translate the wave function of a person's brain into a cognitive state, for instance? I don't know. Look, I don't know how to answer you, Lev. I'm sorry. All I would say is that, look, I know you don't like that. Well, you want to argue for probability just being subjective. All I would say is, look, if the hypothesis that branch rate is objective probability gives you what you want and makes an Everettian many worlds intelligible, then why not adopt that hypothesis? I mean, why give yourself a more difficult, more complicated time trying to think of
words that it's not random, that it does not objective probability. This is why many words is attractive. In the moment you put randomness, why to buy it? This is the whole idea of average. Actual distance and no randomness. And now you why want to spoil many words?
Well, hold on. Where do you think I'm introducing randomness somehow?
What's objective probability? It's not randomness, so I don't know what does it mean. It's not randomness.
No, what I'm just saying. Well, I mean, the hypothesis is that it is just this branch rate. I mean, going back to, so if somebody has a stochastic view, then, you know, thinking stochastically in a fairly straightforward way, then it seems there's objective probability. It seems to be, yeah. So all I'm saying is that in a non-stochastic context, you can have, or in the many worlds context, you can have objective probability as well, and it's just branch rate. I mean, it's out there in the world in just the same sense as it is for somebody who believes in that a lump of radioactive material, it's an objective probability that it's an objective property that it's going to decay in a certain amount of time, or so. It's an, you know, from a stochastic point of view, it's an objective property of that that lump of material. From the many worlds point of view, it's an objective probability. It's an objective property in as much as it's telling you what the branch rates, the decay branch rates are. You know, it's telling you that in a given certain amount of time, there's going to be a certain amount of branch rate, which is in which it will have decayed this much. Or, I mean, if you take a single radioactive nucleus, or a single nucleus of radioactive substance, then it seems to me on the many worlds view, it's effectively branching all the time. I mean, from moment to moment to moment, there's a branch where it decays and a branch where it doesn't decay. And so it's like little fibers of branches coming off all the time. You don't think that, it's not the way you see it?
If I have no detector, there is no branching whatsoever. To have branching, I need a macroscopic detector. Without macroscopic detector, there's no branching. I need the macroscopic.
Yeah, well, okay, sure, but I mean, so we've got this. You've got this single radioactive nucleus, or nucleus of a radioactive substance, with a Geiger counter beside it, and from moment to moment, within minute fraction of a second, there'll be going to be every minute fraction of a second. There's been a branch coming off where the detector fires. And a branch where it doesn't fire, and it'll be. I imagine it is like being a rope, which has little fibers coming off it all the time, and gradually, after the half-life of that nucleus, the rope has sort of got half the cross section because all these little fibers have come off. But there will be, if you've got that set up, there'll be constantly branches coming off, won't there?
No, but they're not will be. They will.
Sorry, Lev.
Yeah, but I think we have to stop here.
Yeah. Actually, I wanted to ask a question to Aurélien as well, but I think Aurélien, we have to keep this thought for 3 weeks, which should be easy. Again, if we don't meet next week, which again, it's I'll let you know. Sorry about that. Anyway, so the idea is that we can have the talk by Lev and then have a discussion sort of comparing the two views. That would be nice anyway. So my question, I think I'll send you an email, Paul. Okay. So yeah, maybe that it interests less people, so I can send you an email. And thank you a lot, Paul. The talk was great. I liked it, and I hope you enjoyed it. And yeah, have a nice weekend as usual. I'll share the recording on Monday. That's it. Thank you.
Okay.
Thank you.
Thanks, Christian. Bye,
everyone.
Thank you.